Today we're going to be taking a look at logarithmic and exponential regression and modeling. So let's dive in, do a few problems. Number 1. Baby blue whales, known as calves, normally weigh about 6,000 to 8,000 pounds at birth. They can grow about 200 pounds per day for their first year of life. The weight of one blue whale is given in the table below, where weight is in pounds and age is in months. A natural logarithmic regression is used to model the weight function. And then we're asked some questions. So let's create our natural logarithmic regression using our calculators. So I'm going to go to my stat mode and I'm going to edit my lists. I'm going to clear out what's there and then get ready to input. So my age is going to be my L1 and the weight is going to be L2. So I'm going to put those in. You put them in your calculator as I'm putting them in mine. We'll try to be as careful as we can. A lot of numbers. Okay, I'm taking a quick look at my numbers, making sure that they are accurate. They look good to me, so I'm going to go with that. Alright, so the natural log regression. So let's go back to stat. I'm going to scroll over to calc, and then LM regression, natural log regression is number 9, so I'm going to hit number 9. I'm going to store the regression equation in for y1 like we did yesterday. And my r squared number is 0.978. That's pretty good, I think. Let's take a look at this graph. So I'm going to go to my window. Let's put in a nice window. I'm going to go from age 0 to maybe age, I don't know, maybe 150 months. Okay, and for the weight, I think I'm going to start at, I could start at 0, but it's looking like since they're 6,000 to 8,000 when they're born, I might start at like 5,000 and end at a big number, maybe even like 300,000. And in that case, I might even just turn off my y scale. I really don't need to see hash marks on my y-axis. Okay, there's that log graph. If you're curious to see where your points fell, remember that you can go and turn on your stat plot and then hit graph, and it shows you where those points are. Okay, just if you're curious, I'm just going to turn that off, because I really don't need to see those points for this problem. Alright, according to the model, how much did the whale weigh at age 5 and 9 years? So I'm going to hit trace, and then number 5, oh, not 5, because this is in months. So 5 years would be 5 times 12 months, right? So you remember, you can just put that right in your calculator. You don't need to do that in your head at all. So at 5 years, the whale weighed about 217,049.47. I'm just going to type in what it says, and that was in pounds. At age 9, I'm going to trace, and then 9 times 12 months. 9 that would be 108 months. 9 years, that is 249,459.07 pounds. And according to the data, that does make sense, of course. All right, according to the model, how much will this whale weigh at 12 years old? At 12 years old, I'm glad that I went to 150. I should have taken a look at that before I started, but 12 years old is 144 months, so it should be on the screen. Otherwise, I'd have to go and increase my window a little bit, or otherwise it would give me an error. So I'm just going to do trace, and then to 12 times 12, that's 144. And at 12 years old, the whale should weigh 265,321.39 pounds. Okay. According to the model, at what age did the whale weigh exactly 100,000 pounds? For that, I'm going to go to my y equals screen and in for y2 or y3, either one. I kind of like y3 because it gives me it in black instead of red. The red from my eyes, it's a little hard to see, so I'm going to do it on y3 where it's going to be black. So I'm going to put in 100,000, and we'll see where those two graphs intersect. So it weighed 100,000 pounds. I just hit, I did that too fast. Second calc 5 for intersect, enter, enter, enter. So it weighed 100,000 pounds at about 7.181 months. Wow, it's a big baby. Okay, number 2. A pump removes water from a tank for 24 hours one day. During this time, the rate of water removal in liters per hour is recorded at various times and written in the table below. An exponential regression is used to model the function r, the rate of water removal in liters per hour, from time 0 to, that needs to be 24. Originally I had it 12, but I changed it to 24. Alrighty, so let's put this in. So I'm going to go to Stat, Edit, clear out what's there. I'm holding down Delete. Hold down Delete until you get that cleared, and then put in your times. That's hours after the time began. And then these are the rates. Take a quick look, make sure they look good. I think they're looking good. All right, and we need the exponential regression model. So I'm going to do Stat Calc. And exponential regression is down under 0. So I'm scrolling now if you want to see what else is here. I'm scrolling. There's several other options. Now that I know it's at 0, I'm just going to hit the number 0 from now on for exponential regression. I'm going to store that in for y1. That's under F4. And that's a nice close to 1 number as well. All right, for a good window, I'm starting at 0 and I'm going to go to, I might go to 30. Well, actually, I could just go to 24 because that tells me, this gave me a time period, so I'm just going to I'm going to go from 0 to 24. For my y min, I'm going to make it, I think I'll make it 0 for my y min, and then for my y max maybe 1500. And I can have I don't need hash marks on my y axis. Okay, very good. So give the value of R of 10. So this is R, and we want R of 10, so I'm going to trace to 10. So R of 10, all right, R of 10 is 533.477. I'm going to give 3 places after that decimal point. And now we want to use correct units and give the meaning of R of 10. So what does that mean? What was R again? R was the rate that water was being removed. So, and what does the 10 mean? The 10 means at T is equal to 10 hours. So at 10 hours, the water is being removed at a rate of R of 10 liters, okay, liters per hour. That's what R of 10 means. At 10 hours, the water is being removed at a rate of R of 10 liters per hour. What is the predicted rate at which water is being removed at 24 hours? So, okay, trace 24. The rate is projected to be 158.024 liters per hour. Okay. At what time is the water removal rate exactly 300? Well, according to this data, it's probably in between 12 and 18, right? Okay. I'm going to go here. Oh, I still had 100,000 in here. I'm going to clear that out and put 300. Second, calc, 5, enter, enter, enter. So at what time? So it would be at T is equal to 16.623 hours. Okay, so that was one logarithmic regression and one exponential regression. Now let's take a look at some various models. Okay, this one is no calculator, so I'm just putting my calculator to the side for a moment. The initial population of bunnies in a park is measured to be 10. It is observed that the population doubles in size every 6 months. Write a function that gives the number of bunnies, B, as an output value and time T in months as an input value. So let's think about that. We want to write B of T. B is the output, so it's the function. Okay, that's the output. Okay. So we are starting with 10 bunnies. That initial I know that this is exponential because it's doubling in size every so often. I know it's exponential. Okay? So in my mind, I'm thinking it's some number times a base to some kind of power with T in it. Something with T in it. Maybe not plain T, maybe it has just something with T in it though, okay? All right, so the initial population will be this thing right here. Because when time is 0, this will be a 1, and that will give us our initial population. So the initial population is 10. Okay, now, this population is doubling in size. If it is doubling in size, that base is going to be 2. If it was tripling in size, that base would be a 3, and so forth. If it was a half-life, that base would be a half. Okay, now, this population doubles in size every 6 months. So this is not just going to be a t up here, because that would have nothing to do with that 6 months. So let me ask you a question. After 6 months, the population doubles. That means now we would have 20. So after 6 months, we need this to be 10 times 2 to the first. So if I make this t divided by 6, will that work? Let's see if it works. T and B, let's make a little table. At time 0, what is the population? At time 0, 2 to the 0 is 1, 10 times 1 is 10. When time is 6 months, 10 times 2 to the first is 20. That's right. After another 6 months, it should be 40, right? After another 6 months, we should double that population, so it should be 40. Let's see if it is. If I put a 12 in for t, I'll have t2 squared, which is 4. 4 times 10 is 40. Yes, that works. So what did we find out? We found out that a population that is doubling will have the initial value, the initial population, I'm going to call that P naught, that's initial population, times 2 to the, this is if it's doubling, to the t divided by whatever your doubling time is, doubling time. Why? Because it just makes sense that it would be that. Okay? Part B. Write a function that gives the time in months as an output value and a certain number x for the population size of the bunnies as an input value. Well, we wrote it the other way around. Now they want us to solve for B. They want us to call B x. I don't know why. I would have been happy calling it B, but they want us to call B x because they told me to. And now they want us to solve it for t. And then at the end I'm going to call it a capital T. So x is equal to 10 times 2 to the t divided by 6. I need to solve that for t. So I'm going to divide both sides by 10. And now I'm going to I'm going to log base 2 both sides. So I'll have log base 2 of x over 10 is equal to t over 6, the exponent. And now lastly, I'm going to multiply both sides by 6. So t will be 6 log base 2 of x divided by 10. Okay, let's look at another one. The half-life of radium-226 is 1600 years. If you start out with 100 milligrams of radium-226, how much is left after 20,000 years? Okay, let's first write our equation for this. It's a half-life one. So, I think I might call this R for radium. R for radium. Okay, your initial population, your initial amount was 100 milligrams. It's a half-life, so the base is a half. And our exponent will be the time divided by the half-life of this element. So 20,000. There's our equation. So how much is left after 20,000 years? That would be R of 20,000. Okay. Pull back out my calculator. Let's see, I might go ahead and put this in for y1. 100 times 1/2 to the t divided by 20,000 And then on my home screen, I can do y1 at, oh my goodness, I just realized, I'm sure in class people would be saying, Miss Murray, that should be 1600. Let me go fix that over here. That should be 1600. That's the half-life, not 20,000. I'm glad they asked me for 20. Okay. So after 20,000 years, we have 0.017, so 0.017 milligrams left. Okay? How long does it take the 100 milligram amount to decrease to 5 milligrams? Well, I could do this a couple of different ways. I could take this, put 5 in for R, and go through the algebra to solve it, but since I have a calculator in my hand, I'm going to use it. So I have the graph here, okay? Well, I have the equation there. We are starting with, well, gosh, let's see. I might go from time, the x is my time, right? I might go from, I might go from 0 to, I don't know, 10,000? Turn off my x scale. And from 100, oh, I'm sorry, my minimum is 0 to 100. Okay. Alright, there's my graph, and I want to see when will that graph be 5 milligrams, so I'm going to do y, under another y, I'm going to put 5 in, and second calc 5, enter, 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 that is 6915 years. It's a long time to go to 5 milligrams. Okay. Alrighty. FYI, a little tidbit of information there for you to read. Okay. A 50 milligram dose of a drug is administered to a patient. 2 hours later, the amount of the drug in the body is 25 milligrams. The amount of the medicine M in the patient's bloodstream can be modeled by the exponential decay function M of t is AB to the t. At what time will the amount in the body be 1 milligram? Okay, so the amount of medicine at time t is, okay, since this is a plain t here, what is the initial amount? Well, the initial amount was 50 milligrams. I don't know the base. I don't know the base. So I need to go find the base, and I can find the base using this information. 2 hours later, the amount of drug is 25 milligrams. So when t is 2, the amount should be 25 milligrams. So I'm going to put 50, I'm going to put 2 in for t. That should be 25 milligrams. So b squared should be, if I divide both sides by 50, b squared should be a half, and b should be the square root of 1/2. So now my function is m of t is 50 times the square root of 1/2 to the t. Okay? At what time will the amount in the body be 1 milligram? We want to know when is this equal to 1? And I could do this with my calculator. I could do this by hand a little bit. I think I'm just going to use my calculator. I'm going to put this equation in for y1, and I'm going to put 1 in for y2, or a different y, and use my calculator here. This is square root of 1/2 to the t, I'm going to call that x, yeah? And now I want to see where these two intersect. I think I might just try zoom 4. Not so lucky. Not so lucky. I'm going to trace, see where I'm at. Okay, for my x-min and x-max, I'm going to go from 0 to, I don't know at all. This is in hours. I might go to 20 hours, 24 hours, something like that. And for the y min and max, I'm going to go from 0 to the amount that we started with, 50. Much better, much better. Okay, so second calc 5, enter, 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 and it's at t is equal to 11.287 hours. Okay, number 6, no calculator. The last two of these problems are no calculator. A decibel dB is a unit of measure for the loudness of sound. The decibel scale is based on sound intensity N in watts per square meter. A decibel value is given by the function d, where d of n is this equation. What must be the sound intensity, that's n, what must be n in order to yield a decibel of greater than 90? We want this thing to be greater than 90. This is about how loud a lawnmower is. So I'm going to take this equation and set it greater than 90 and solve for n. It'll give me an interval. Divide both sides by 10. I'm going to write this is bothering me, I'm going to write this as n times 10 to the 12th, and that should be greater than 9. Okay? And now I'm going to take 10 to both sides. 10 to both sides. So I'm going to have just my exponent, n times 10 to the, not exponent, argument, just the argument, n times 10 to the 12th is greater than 10 to the 9th. Now I'm going to divide both sides by 10 to the 12th. And I get n is bigger than 1 over 10 cubed. So that means n is bigger than 1 over 1,000. Alrighty. Number 7, last one. A disease affecting a certain type of fish in a lake is spreading at a rate of 13% per day. 50 fish are observed to have the disease on day 1. So 50 is our initial amount. Okay, which of the following functions gives the number of fish that have had the disease after t weeks? And I notice that it says weeks, not days, and that bothers me because they gave me the rate in days, and now they want me to have t in weeks. Okay, so the way I'm thinking, my thought process is this function is going to be my initial amount, 50, times some base to some power, right? So in my mind, I'm not going to bother with the weeks quite yet. I'm going to do this with days, and then I can easily change days to weeks. But first I'm going to do it a day because they told me this rate in days. Okay, so after 1 day, you agree that we would be multiplying 50 times what? 50 times what after 1 day? How many fish have had it after 1 day? Well, after 1 day, I need to multiply by 1.13 to get after 1 day. That would give me a little bit more than 50. If you just do it by 0.13, you're going to have fewer fish with the disease, and that's not the way it's happening. Okay, so I know that is true. So if I just have it a t, if my first thought is, let's see what happens if I just have a t there. If I just have a t there, after 1 day, I would have the right amount. After 2 days, is that still the right amount? I would be taking my day two amount, and I would need to multiply by another 1.13. This is going to work. This is going to be my function in days. That's in days. I want it to be in weeks, so I'm going to change this to weeks. So 7 days equals 1 week, right? So my days, this is in days here, my days will be 1/7 weeks, right? So I need to divide, if I'm changing this to weeks, I need to divide it by 7. Yeah? So let's check that. Let's see if it works. After 1 week, 1 week would be 7 days. Is that right? Ooh. No, that's not right. That is not right at all. If I want weeks, I needed to multiply by 7. I need this to be multiplied by 7, right? After 1 week, that was 7 days. That's what I need. I need 7 times W. It does help to finish this off with a logic, just is this going to work kind of thing. So I need 7 times the number of weeks. So the correct answer here would be C. Okay. Logarithmic and exponential regression and modeling.